Hello. Hello, everyone. Okay. Yeah. We are about to start, I think. So I'm Hao Shufang, currently a postdoc at MIT with Phuket and TED. So today we are going to continue our course on modern robot learning, hands-on tutorial. Yep. So let's do a quick recap. On Monday, Yang Hyo talked about data collection with teleoperation, and he covered 4 key elements, which are designing commands for humans and convert commands to robot action, designing feedback to human, and convert robot perception to human feedback. And Yang Hyo also briefly talked about simulation, and he mentioned about how to solve the real to sim issue, which is to build environment in simulation from real world perception. And also he talked about sim to real issue, which is about how we can transfer policy trending simulation to the real robot. So today we're going to talk about the other 2 approaches of data collection that can be applied for robot learning, but without requiring a real robot when we are collecting the robot data. So these 2 approaches include learning from videos and also learning from interaction interfaces. And here is an outline for what we're going to cover today. So first, we're going to talk about learning from videos. And in this section, there are 2 parts, namely how we're going to learn policy from human video. And we'll cover about the observation mismatch issue and also the action mismatch issue. And then we're going to talk about world modeling, which is utilize all the video data on the internet to train a world model. So it does not require the video with a human in it. And then we'll talk about drawbacks of all the 3 data collection approach we have covered, namely teleoperation, simulation, and video. And we will move to a new direction of data collection, which is to build interaction interface. Okay, so now let's begin with learning from videos. So in this section, there are 2 things as mentioned. One is how we're going to learn a policy from human videos. And another part is how we're going to learn a world model from all possible internet videos. So for the first part, if we're going to learn a video or learn a policy from human video, and on Monday, I think Yang Hyo mentioned how to train a robot policy. So to train a policy, you basically need observation of a robot and action information for a robot. But in terms of human video, we actually do not have the observation for robots, and we do not have the action for robots. So that is the observation mismatch issue and the action missing issue. As we can see from the right images, so we have many people doing for example, daily life in kitchen. But although people is doing action, we do not have the real action for robot, which is the torque and the joint position that the robot needs to send to each actuator to move to a certain places. So now let's look at the first issue. Oops. How can I make this smaller? Okay. The first issue is the observation mismatch. So in this figure, you can see that in the left one is a human doing daily manipulation. So in the image, it's a human hand. But when we are trying to deploy the policy for robots, what the robot see is actually the right image, a robot arm there. So we can see it's actually pretty different. And if we just train a policy on human video and transfer it directly to a robot, the network's gonna perform pretty bad because it doesn't have you haven't seen such kind of data, or the data distribution is different. So in one paper, in EgoMimic, so the researchers proposed a way of masking out both human and robots from the image, as we can see from the right side. So we can see actually the human hand and the whole arm is masked out by some off-the-shelf computer vision model. So I guess you have heard of segment anything or SAM. So basically, it's like a segmentation model that does not need any training and can be applied on any images as long as you specify the target where you want to mask out. So we can just specify, like in the left image, oh, we want to mask out the human hand. And in the right image, oh, we want to mask out the robot arm. And it turns out that both these two areas will be blacked out, or like masked out and turns black. And then the researchers also like add a red line here. And in this way, like the morphology gap is like decreased because now the network's attention will be largely biased towards the red bar or red line. And in this way, like we can assume the policy trend with human video can be transferred to the robot, like in a better manner. So here's another example of like how we can deal with the observation mismatch issue. So in the DexCap paper, imagine if you already have the action information for the robot, like which we will cover later. So if you have the action information for the robot, you can actually render the robot images or point cloud to the like human video. So in this example, in the top right image, so it's actually the point cloud that is captured by the RealSense camera of the human video. So it's a human hand there. But then since we can retarget the human action to robot action, we can actually render the robot hand onto the scene, which is shown in the bottom right image. So if I don't tell you, like, probably you cannot see or you cannot tell whether it's like a robot hand or a human hand. So that's basically the intuition behind that. You just render the robot onto the scene, and it can just basically like rewrite the image or like give the robot an illusion that it's watching itself. Okay, so by retargeting, we can now get an observation close to the robot would have. That's good. But now another more important issue is we don't have the action data. And for action, we mean like the joint position and the torque. So how are we going to solve that? Well, if we look at all the current data we have, so we have a human video. In order to get robot action, there are actually two steps. For the first step, we need to obtain the human action from human video, which is like from D1, we need to transfer it to D2. And after that, we can like obtain the robot action based on human action. And that involves two mapping. The first mapping is to map human state or human images to human action. And the second step, we will need to transfer the human action into a robot action. And let's look into these two steps separately. So for the first part, well, actually in computer vision area, there's one topic called human pose estimation. And the idea of this area is like, and they will like specify the key points on human body. For example, the key points are usually the joint, or like, the joint of humans. For example, our elbow, our wrist, our knuckles. And then it detects these joints. And also like after you have the joints, you can connect all these joints and it will form the skeleton of the human. And based on this, like, it's actually not the action, but it's like a lower state, a lower dimensional state. So now, like for each human, instead of the raw images, the state action, the state space will become like about 17 degrees of freedom, depending on like how many joints you want to define for each person. And based on that space, you can like, if you get the difference of two states based on human joints, then you basically get the action information for human. And similarly, you can also get the action for dexterous hand based on computer vision technique. So here I would like to show a video. So you can see that in this video, there's a human mesh or hand mesh rendered onto the scene. And we can actually see it's very accurate and it's very tracking stably. So we also have some example of like human doing more fine-grained manipulation and with hand tracking. Yep, and similarly, so for the previous examples, they were all key points or actions in 2D. But for robots, we also need actions in 3D. And thanks to the computer vision technique, it's also possible. So there's also another area named 3D human pose estimation, which is to lift the 2D key points into the 3D space. And here I show two examples of how that will work. Yeah, so based on this technique, we can now transform the human images into human actions. And now the next step is about how we're going to transform the human action into robot action. And this area is called action retargeting. So the idea is simple, so now since we have the joint or the end link position of the human hand, we can also specify a reference frame on the robot. And then just by computing the relative distance between each corresponding joint, we can compute the robot kinematic through inverse kinematic. And here is the example of how we can get the robot action from a human hand or human action. So in the left image, there's a glove which is recording the human action. And that glove can be also replaced by computer vision technique, as we just mentioned, to recover the human hand mesh or hand pose from a video. And through the retargeting, we can get the robot joint as shown in the right image. And we can see it's actually pretty accurate. But this approach also has its limitation. And can anybody tell the limitation is? So actually, if you see the green, red, and blue dots, so that's the position that this action retargeting is target for. So it basically maps those end position to the same, or as close to the human action. However, when a robot is interacting with the environment, we are not just interacting with the environment with our fingertip, but we are also involved the other part, for example, the palm and the middle part of our finger, for example, when we are grasping something. So the limitation of this kind of action retargeting is always the action is not very accurate. It's just a rough action. Yep, so now by action retargeting, we can get the rough robot action, and which is the joint position. Now the question is how we can learn from this data. So there are actually 3 ways we can learn from this kind of human video data. So since, as we mentioned, the input, the observation is just a similar observation, it's still not the robot observation. So there's still some domain gap. And for the action, it's still rough action, it's not very accurate. So we still kind of need some sort of robot action or robot data to train with the human data. So the first way is to pre-train a policy based on human video and human action. And then we fine-tune this network based on the robot data, which takes the robot observation as input and then output the robot action. And the former data set is collected by the method we just introduced from online video. And for the data set used for fine-tuning, it's still we need to collect the data from teleoperation, which is introduced by Hyung-Hyo on Monday. And another way to combine human dataset and robot dataset is to do a mixed training. So in this example, like we can input the images of both human and robot into the same network. And the network will also output the human action and robot action in the simultaneously. So all the training data goes in one batch. And in this way, like the network is forced to learn, for example, how to move the end effector regardless of the embodiment. The third way is like we still train the robot or the policy based on the rough robot action we just mentioned, based on the human observation. But since the action is pretty rough, it cannot be directly applied to the real robot. So we still need a second post-processing, which is like human-in-the-loop correction. So that's still kind of like the first approach, which is to pre-train the network and then fine-tune it. Okay, so far we have introduced how we can learn like policy from human video. But the problem is there are actually so many videos in the internet. How can we utilize them? So we're gonna introduce the second approach, which is world modeling from all videos. Yeah, as mentioned, like there are many different videos. So most of them does not contain humans. So we cannot recover the human action and we cannot get the robot action. But these videos are actually pretty useful because they contain the information of like physical interaction, and it can help us to model like how the robot can interact with different objects in the world, in the pixel space. So this is what the Gen AI people do. I guess you all have heard of Sora, which is from OpenAI. And what they did is like they would train a foundation model, a video foundation model, which like just predict or just generate a video that's very vivid. So here are some examples generated by Sora. And the idea of using this method for robot learning would be very intuitive. So in terms of data, we just need like all internet data, all internet videos, and we can also have videos, or have like data from games. And in terms of learning, so here's the formulation. So a network basically takes a language instruction, for example, an author is surfing, or a current frame. And then the network will be like trained to predict some future frames. So this is a very straightforward training method. And based on that, we can apply this approach to robotic manipulation. So here I show some examples from Cosmo, which is a recent foundation model from NVIDIA. And they basically like take the idea and apply it to robotics. So they train the video generation based on a lot of robot videos. So in the first example, the language instruction is for the green fabric item on a table. And you can see the predict video looks pretty good, right? So it looks like almost real-time execution. The second video is organize books. Oops, sorry. Yeah, the second video is organize books by placing them vertically on a shelf. So it's also like generate videos in a very high quality. The third example is pick up an electronic device from a table and place them in a bin. Well, we can see that the physical interaction is still pretty well. Like when the robot picked an object and lifted it from the table, the object actually like follows the end effector of the robot. That's also very impressive. But what's the problem of applying this approach to manipulation? Do you foresee any? Oh, yeah.
Are these videos of like the robot in simulation, or is this like the real robot?
Oh, they are all real robots. Yeah. So actually, this robot is called 1X, and The idea is like they first collect a huge robot data set through teleoperation. And then like they train a model that takes the language instruction and predict the future frames of the robot. Yep. Yeah, answer?
So are all three of these videos like generated?
Oh, yes. Yeah. So these all three videos are generated. And we can see actually they have pretty high quality.
It's not like Cosmos produced some model and then we ran on a real robot and then this like the real robot.
Yes, exactly. This is, sorry, I was saying this is just the image, the videos generated by Cosmos. Yeah, this.
Is this a video taken from like a robot in real life?
No. They are all, well, not in simulation, but generated. Yeah. So, but they look so real, right? So it's very impressive. But do you see any problem of applying, how to apply this to manipulation? Answer?
I mean, like, I guess the physics isn't perfect. Like in the third video, the icon floppy whenever the robot picks it up.
Yeah, exactly. So that's one point. For example, if we look at this video, like it should be a rigid object, but in the second half of the video, it seems the object start to deform, right? So that's one problem. And do you see other problems? Okay, so actually the most critical issue is it doesn't have action information, right? So although we can foresee the future, okay, we now know like what the future images will look like, but how are we gonna guide the robot to achieve those future frames? So that's actually two different questions. So now we need to actually get or recover the action information from the predicted future frames. And so in order to get that, there are two ways. One way is to learn an inverse dynamic model. So the idea is we still need a robot data set and probably collected by teleoperation. And then we train a network that takes two observations, well, in 2 frames or in 2 time steps. And then the network is trained to predict an action that can guide or allow the robot to like transfer from the first state to the second state, which is from the first image to the second image. So this is called, as I mentioned, an inverse dynamic model. So the problem of this approach is that we still need a robotic data set collected by teleoperation, which is what we are trying to avoid, because now we are talking about, we hope to just learn action or allow the robot to directly manipulate from video data. So there's another way, which is just to learn a correspondence. And the good thing is, so this correspondence can actually be obtained through like some library like OpenCV, and it's a very mature area, so we don't need to train specifically for this task. So now we have like synthesized future video, a couple of images, and then we just like compute the optical flow based on 2 images, and based on the optical flow, we can actually like compute a correspondence to the robot arm. So the idea is just like to compute a matrix that will allow the robot to achieve such kind of optical flow based on the predict one. So in this way, we can guide the robot to accomplish the action. Yep. So now we have covered talked about how we're gonna learn, how we learn from video for robot manipulation. Any questions so far? Okay, sounds good. So now we're gonna move to the second part, which is I'll talk about the drawbacks of all current like data collection methods we have introduced. So far, Yang He talked about teleoperation simulation, and we just covered video, learning from video for robot manipulation. So what's their problems? As we mentioned, like to train a policy, we kind of need the observation data and action data. So for teleoperation, we have these two kind of data. But the problem is, so the first problem is it's very expensive, and we need to ask a bunch of people to collect the data. And I think Yang Yu also covered this part on Monday. But another more critical issue is that teleoperation is actually pretty inefficient, and its capability is pretty limited. So here I would like to show you a video, which is a failure case from Avatar Prize. I think Yang Hill also showed some video from Avatar Prize on Monday. So the background is that it's a challenge where the first place can win $5 million. So all these teleoperation platforms, they are all well engineered because the price is so high. And in this video, you're going to see the teleoperator trying to teleoperate a bimanual robots to use its dexterous hand to grasp a drill and then to open a door. So how many seconds does it take to grasp the drill? I have been talking about 20, 30 seconds, I guess. So now it just finished, grasp the drill. And imagine, how many seconds do we take to grasp a drill? Probably 2 or 3, I guess. So that's the first part. It's very inefficient because the teleoperation naturally introduced some mental burden for the teleoperator. And now, let's look at this part. So when we are teleoperating the robot, we will definitely run into some failure cases. For example, in this video, the robot ran into the wall, so the drill just get loose from the hand. So we need to now adjust it. And now the human teleoperator is trying to adjust the drill based on teleoperation. And let's see how long it takes. It has been 30 seconds. Okay. After 40 seconds adjustment, the drill still falls to the ground. So now you see the problem. Oh. Yeah, let's look at it again. Failed. So that's the critical issue of teleoperation. For many tasks, it actually takes much longer time to collect the data, and you cannot accomplish many tasks in a very good way. So that's the problem of teleoperation. And how about simulation? Well, if we want to build or train or collect data in the simulator, what we need to do is we're going to need to transfer or build many environments in the simulator. And just imagine, or look at our daily lives. If we want to build all these different environments in the simulation, it's going to take us a huge effort to build a simulation counterpart. And also, the problem is it cannot scale in task level, because every time we want to build an environment in simulation, it requires a PhD or a well-paid engineer to do this stuff. So we literally cannot build so many environments that's even close to what we will encounter in our daily lives. So in terms of learning from video, as we mentioned, So for the observation space, it only contains visual observation, right? So there's no tactile feedback. And if the video is heavily occluded, then like we might have the trouble of like we cannot actually recover the action from the video. And actually for GenAI, it's also not perfect. So in the right image, I show an example where I ask a GenAI to generate a video where the robot arm pushes the red block. So you can see actually it's not following the command. And actually, like for some reason, the table is like just shaking around. So it's still not perfect. And that's the problem of learning from video. So we actually need a new paradigm for data collection. And what is that? So when we are talking about like collecting observation and action data for agents, there's actually one kind of special agent, which is human. We are doing manipulation all the day, like every moment. So we can like go to the assembly line, we can do cleaning, we will do lab, and all these data are generated, but they are just not recorded. So if there is some device or there's a way to collect observation and action data, so we can use this data set to train the robots. So here I would like to introduce the concept, which is interaction interface. So they are like devices that can record observation and action data when humans are interacting with the world. So now, for the next part, we're gonna have a case study for the interaction interface. First, I'll show 3 examples of interaction interface, which are, the first one is AirXO. It's an exoskeleton where you can wear. And on the exoskeleton, so there are some like joint encoders, so you record the robot action. And also there are 2 cameras attached, but you cannot see from this video. So for the second video, it's called UMI, like Universal Manipulation Interface. So it's also similar, like there are 2 cameras attached to the gripper, and they'll recover action from like the GoPro through like SLAM. The third one is called DEXO, which is a dexterous exoskeleton to collect like human-robot interaction data. So first I'll show some example of how people collect data with AirXO and UMI, and later I'll introduce or go into details of how to build this kind of interaction interface through the DEXO. So for the AirXO, we can actually see people can wear it and do many different tasks. For example, rearrange the tube, do soldering, fold the clothes, or like fold the cardboard. For UMI, it's also similar. Like you can have 2 gripper and you use them to fold the clothes or adjust or rearrange the table. So the observation data is actually recorded. You can see here, there are 2 cameras at the back of AirXO and 2 cameras on the gripper for UMI. So now let's delve into the details. So in terms of this kind of interaction interface, what is needed and how are we going to achieve that? And why is the interaction interface a better option than teleoperation? So in order to collect data, as we mentioned, we need observation data and we need action data. So in terms of in terms of observation, beyond visual observation, another important modality is tactile. So here I would like to show you a video. So in this video, a scientist is injecting some drug to a human participant's hand, which would numb their sense of touch, but the hand can still move freely. So now, this human subject is trying to strike a match based on pure visual feedback. And we can see that for this simple task, without tactile feedback, it actually takes her 30 seconds to accomplish it. Yeah, so now you see how struggle it is to accomplish some task without the tactile feedback. So we also want the interaction interface to collect this kind of tactile feedback for robot. And for action, well, beyond the position, another important action is torque. So for example, imagine we are holding a bottle. If I just give you the position of the hand, you cannot like if you don't apply force, the bottle is gonna just slip away from your hand. So that's why torque is also important in action. And lastly, we need to remember that the data collected from this interaction interface needs to be deployed on real robot. So we also need to mitigate the embodiment gap from a human hand to robot hand. So based on these principles, how are we going to achieve that? Well, if we look at this figure, so for human hand, and we want to somehow bridge the human hand and robot hand. So when we build the interaction interface, you actually have constraints from both human hand and robot hardware. And since we cannot adjust our human hand, we cannot just cut off some fingers, we need to have a co-design of robotic hardware and interaction interface so that both these two hardwares can comply with human hand better. So the first thing is we need to have a robotic hardware that is closer to human hand. Okay, so here I would like to introduce EyeSight hand. So for this hand, the researchers built a tactile sensor, which is pretty close to human tactile sensing. Well, actually, the first author is right there, Brandon. And the idea is that if we incorporate the tactile sensing, this is a vision-based tactile sensor. The idea is just put a camera underneath your finger. And you can see the fine-grained geometry of the object that it is touching. And you can also see the shear force by tracking the dots on that surface. So this is the first thing, make tactile sensing closer to human. And the second part is to make dynamic closer to human. So this hand is incorporated with proprioceptive actuator, which allows the hand to backdrive when it collides with the environment. And the hand can also move pretty fast, agile as possible to catch the flying bottle. So the third thing is to make the form factor close to human hand. So this hand, basically it has a similar size to your hand, and the degree of freedom is also positioned put in the right position as close as possible to human hand. So after that, since now we have a robot hand that is pretty close to a human hand, we can just build the interaction interface to bridge human hand and robot hardware. So the idea is also pretty simple. For the actual hand, this figure shows the CAD model of an actual hand. We can remove all its actuator and then put joint encoders at its joint. The joint encoders is enclosed by the red circle. And now we have a passive hand. So this passive hand can actually have all the sensors, all the sensing that an actual hand would have. It had the full hand tactile sensor, and the joint encoder will encode the joint position. So now we just need to drive this passive hand when we are trying to manipulate object. In order to achieve that, we first build a wearable exoskeleton. So this part is somewhere you can place your hand at. And we then build some linkage systems to connect the wearable exoskeleton and the passive hand. So when you connect them, it has two advantages. The first advantage is that the linkage can transmit the force from the robot to human. So when the robot hand is interacting with the environment, when it collides with the table, the force will directly be transmitted to human's hand. So now you will have haptic feedback when you are trying to do a teleoperation, or daily manipulation. And the second benefit is it reduces the DOF from 21, which is the degree of freedom of human hand, to 7 degree of freedom. So that's pretty good because we want the action space to be aligned with the robot. And this interaction interface can also achieve that. So here I would like to show you a video of what this kind of interaction interface could do. So in this example, the goal is to assemble a robot finger by wearing the exoskeleton. So it involves multiple steps, and they are actually quite dexterous. So you have to open the box and pick up the tiny box which contains the camera, and then you close the box. So here, when you are trying to open the small package, you can see that it's actually heavy occluded, which means if you just want to learn this policy from human video, you cannot actually recover the accurate action information, right? But with this kind of exoskeleton, you do not need to recover those action information through through computer vision. You can just directly record them through the joint encoders. And in this part, you need to squeeze out the camera from a plastic bag. So how to simulate this kind of deformable plastic bag in simulation is also another problem, which is why simulator can be hard to collect data for this kind of task. And you can also press fit the camera into the finger. And this actually involves quite a large force. Okay, now here it is the very dexterous part where you need to open a small box and take the screws out of it. Okay, you got the screw. You just place it in the right position. Okay, last, this is the manipulation which involves tool use. So you just pick up the drill and drill the screw. So remember like how long it took for the teleoperator to hold or to grab a drill, and just compare it with how long it takes with the hand exoskeleton. Yeah, basically just take like 5 to 6 seconds to accomplish or to like grasp the drill. Oops, sorry. Yeah, so now we have this kind of device that can record observation data and action data. And how are they compared to the real robot data in terms of observation and action? So in the observation space, we have the same tactile sensing as the real robot. And if we put a wrist camera on both exoskeleton and real robot, they will also have the same format. The only difference comes from the head camera, but there are actually some ways to solve that kind of observation mismatch issue, as we just introduced at the very beginning of our class. So in terms of action data, now we have the accurate joint position, and also the torque can be computed from the tactile sensing very easily. So now basically we have very good observation and action information. And why is this like exoskeleton better than teleoperation? So we conduct a user study on 6 challenging tasks involving like bottle opening, bulb installation, box packaging, drilling, hard disk assembly, and cardboard folding. So we invite 4 human subjects, and they'll accomplish each task by teleoperation and also with exoskeleton. So in this figure, we show the efficiency or like task throughput per task. So the red bar is actually the efficiency of human of data collection through teleoperation, and the blue bar is the efficiency of exoskeleton. So we can see that actually on the first 3 tasks, exoskeleton can achieve 2 to 7 times more efficient than teleoperation. And for the last 3 tasks, well, teleoperation cannot even accomplish the task. So in terms of policy training, after we have all those like data collected through interaction interface, how are we going to train the policy? So there are 2 ways. One way is if like there is a huge visual observation mismatch issue, we can adopt the pre-train and fine-tune paradigm. So in this example, like the human subject is collect some demonstration with the exoskeleton. And we can see that the visual observation is different. So we can first pre-train the policy. And then we can fine-tune this policy based on some like small amount of teleoperated data. So this is one way to accomplish that. Another way is, since we have aligned the observation space and action space, we can directly train the policy based on the interaction, the data collected by interaction interface. So in this UMI paper, they mount the camera to on top of the gripper. So which means for both interaction interface and the real robot, they share the same visual space. And also like for the action, they just recover the 2 Cartesian poles from the IMU sensor on the GoPro. Yep. So we also talk about how we're going to learn the policy. And today we covered like learning from video, which covers 2 parts, namely policy learning from human video, and also work modeling based on all kinds of internet video. And we talk about drawbacks of 3 different methods, include teleoperation, simulation, and learning from human video. And we introduced a new paradigm, which is interaction interface. And we also showed like how we could build such kind of interaction interface. And lastly, we covered the policy learning with interaction interface. And that's basically all for today. And for the next class, we will have a hands-on tutorial on how we can collect data in simulation, and how we can collect or build a data set and train the policy, and how we can evaluate our policy on the real robot. Yeah. Any questions so far? Answer.
So out of curiosity, would you say that you noticed any weaknesses of the interaction interface, sort of like way of collecting data?
Yes. So now I think there are 2 main issues. One is it still takes some efforts to design such kind of interaction interface. So as you could see, like we have very, as you could see, we have very like complex linkage systems, and we also need to design the wearable exoskeleton to have the same kinematic as the real robot. And this actually takes also quite a bit effort from a PhD or like engineer. And also for each kind of different robot, for example, robot embodiment, we need to build such kind of interaction interface respectively. So that's one part. Another thing is, like when we are collecting data, the visual observation is still like has some mismatch issue with the real robot. And that, although it could be solved by, for example, pre-train and fine-tune paradigm, like it still require you to collect a data set, for example, with limited amount of teleoperated data. Yeah, so that's 2 main issues that I could see. Yeah. Any other questions? Yeah.
For the 1x world model, why don't they just predict the drone angle along with the because they do have a drone.
Yeah. So actually, they don't do that in the Cosmos, but there are other researchers doing it. in a similar way you mentioned. So I think the reason for Cosmos is they build it like a product in NVIDIA. So the idea is they pre-train a huge video foundation model based on all internet data or video, and then they could allow you to fine-tune it on different robots data set. So they just use that as a showcase, I guess, for the 1X example. But it's definitely doable if you want to also include the action information when you are predicting the future. And I think the paper is called GR1. So in that paper, the researchers showed that if you co-train the action prediction with the video prediction, you can actually also gain some performance improvements. Yeah. Sorry?
What is the paper called? You just mentioned?
GR1. GR-1. Yeah, I think it's from ByteDance. Yeah. Yeah. Any other questions? Oh, if no more questions, I think that's all for today. Yeah, and I look forward to seeing you on Friday. Yeah, thank you. Yeah, hi.
I'm new to this class. I just signed up. But I looked over the past 2 lectures on the website.
Yeah.
How do you get graded for this class? From my understanding is we have 4 lectures.
Yeah.
And then we have a project.
Yeah, exactly.
Okay, sounds good.
Yeah.
So is there anything like I missed?
Not really. The grade will mostly based on the project. Yeah, we don't have homework.
Okay,
Yeah.
sounds good.
Yeah.
Thank you so much.
Yeah, no problem. Yeah, hi.
I was just wondering, after the lectures, Friday's the last lecture, and after that, what is the concept of the class? Like, what are we supposed to do?
Oh, it's that's what we will introduce in next class. So basically, it will be a hands-on project where you need to collect data in simulation and train a policy and deploy on real robots.
I see. And do we do it by ourselves, or like in a group?
In a group. In a group.
All right, thanks so much.
Yeah, no problem.
Okay, make sure you record everything. Okay, can you send me the video later?
Yeah. Oh, hello. Oh, yeah, by the way, since we still have an hour left, so if any one of you is interested in seeing the exoskeleton, we can have a lab tour. I can show you the exoskeleton. Yeah, that's it. What did you say, Arthur? Oh, I see. Yeah, I think so.
I'm interested.
Oh, yeah, sure. Yeah, see you.